How can a picture survive when you throw away 99% of it? Watch. Each step adds a few more numbers, and the planet pulls itself back together out of almost nothing. Before any of that, one thing in case this is the first video of mine you have landed on. You need no maths for this next part. Zoom right in on any picture, and there is nothing clever in there. It is a grid of brightness values. One number per pixel. That is all a photo has ever been, and all a matrix is. Now the one idea this whole episode runs on. A layer is not a piece of the picture. A layer is one row of brightness, one pattern, and a dimmer setting for each row. Copy that one pattern down the picture, turning it down a little each time. That is a layer, nothing else. Watch it fill in. Row 2 is dimmed to 0.96, so 0.96 times 146 is 140, times 169 is 163, and so on, every square, just one multiplication. Fill the rest and you have rebuilt a whole block of the photograph out of 4 numbers and 4 dimmers. It is not perfect. Compare it to the real pixels and it is about 9% off. It catches the broad shading but loses the detail, which is exactly why you stack more than one. Mathematicians write that like this, and if the symbols mean nothing to you, ignore them. They are only names for the 3 things you just watched. The patterns, how loud each one is, and the dimmers. And the stretch factors in the middle, the singular values, come out sorted. Biggest first, and they fall away fast. That ordering is the whole of today. Here is the idea the whole episode rests on. That 3-part product can be rewritten as a sum. One term per singular value. Each term is one layer, a single, very simple image. On its own, each looks like nothing, stripes and smudges. But stack them, layer 1 plus layer 2 plus layer 3, and a picture starts to appear. The matrix is that stack, and the singular value in front of each layer says how loud it is. Summarize a 2-hour film, and you do not keep every frame. You keep the 5 scenes that carry the story, and anyone who hears them knows the film. The rest was detail you can lose without losing the plot. But why should a photograph be squeezable at all? Noise is not. These are the real singular values of the photograph from the opening. Look at the shape. The first one towers over everything, and by the 10th, there is almost nothing left. So a handful of layers carry the picture, and the long tail is detail almost nobody would miss. Hold on though. Why should any of this work? Here are 2 images. The same size, a photograph, and pure random static. Now look at their singular values. The photograph falls off a cliff. The first few carry almost everything. The noise is flat. Every direction matters exactly as much as every other. 10 layers hold 95% of that photograph. The noise needs over 100 to reach even 90. So compression is not really about images at all. It works because the real world has a structure. And structure is exactly what a few big singular values mean. Randomness cannot be compressed. Cut the sum short. Keep the first k layers, drop everything after them, and call the result A sub k. And now count what you actually store. Not the whole grid, just k columns, k rows, and k numbers. 20 layers of that photograph is 9% of the original file. Pull up an equalizer on any song, and almost all the energy sits in a handful of bands. Mute the rest and it still sounds like the song. The singular values are that equalizer for a matrix. And here is the part that makes this a theorem rather than a trick. Out of every possible rank K matrix in existence, this one, the one you get by just truncating the sum, is the closest to the original. Nothing else is nearer. It is called the Eckart-Young theorem, and it even tells you the error in advance. It is exactly the singular values you threw away, which is why dropping tiny ones costs you so little. So what is that actually worth? Watch a real photograph pay for itself. 1 layer, 0.5% of the file, and it is a smear. You would never call that a planet. 3 layers, still a blur, but something round is forming. 8 layers, 3.6% of the file, and you can already tell that is the Earth. 20 layers, 9% of the storage, and there are the continents, the cloud systems, the terminator line. 50. At this point you have to look hard to see what is missing, and 120 layers is, to your eye, the photograph. That is the whole of low rank approximation. 9% of the numbers carried essentially, all of the meaning. One more thing, because almost everyone gets this wrong. People assume compression means throwing away pixels. So let us spend the exact same budget both ways. On the left, keep 9% of the pixels and bin the rest. On the right, keep 20 layers, the same 9% of numbers. 95% error against 17. 5.5 times better from the same number of stored values. Because a layer is not a piece of the picture, every layer touches every pixel. You are not keeping parts of the image. You are keeping the directions it is built from. And this is the part that reaches all the way into ChatGPT. Here is one weight matrix from a large model, 4000 by 4000, nearly 17 million numbers. Fine tuning normally means retraining all of them for every matrix in the network. LoRA says leave that matrix frozen. Never touch it. Instead, learn a small correction beside it and force that correction to be low rank, exactly like the layers we just kept. Two skinny matrices, B and A, count them. 65,000 numbers instead of 17 million. 0.39% of that matrix, and across a 7 billion parameter model, LoRA typically trains well under a tenth of 1% of it. The photograph you just watched rebuild itself, and the way people fine tune a giant language model on a single graphics card are the same piece of mathematics. And because the big matrix never changes, you can keep one copy of the model and snap different little adapters onto it. One for medicine, one for law, one trained on your own writing, each a few megabytes instead of a few gigabytes. 4 lines. Take the SVD, keep the first K of everything, multiply back. That is the best rank K approximation there is, and the notebook does the whole photograph plus the error curve. The map. Today, a matrix is a stack of layers ordered by importance, and you can stop early. You are here. What it buys you. A matrix is a sum of layers. Biggest first. Keep the top few, and Eckart-Young promises it is the closest copy of that size. And that single fact is both image compression and LoRA. One episode left. We turn the same idea on your data instead of one matrix and see how an AI looks at 1,000 dimensions. Next, finally, the same idea turned on your data. Instead of one matrix, how an AI looks at 1,000 dimensions and actually sees it. Thanks for watching and keep exploring. Next time, PCA, how AI sees 1,000 dimensions. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.